Welcome to example 18 in functions and graphs. We're doing a bit of graph sketching here. We're going to sketch a graph of a rational function. I would say in the advanced higher course they no longer have a full graph sketching question. So examples 17 and 18, you wouldn't see this as an exam question. But what you do have to be able to do is to understand the different parts of it. You have to be able to study asymptotes. You should be able to discern turning point. So it makes sense just to put it together in a performance, even though in an exam it might not be there, but it helps us to show how all the parts come together. So I still like being able to teach it and expect it to be done in full. So if sketching the graph of a rational function, we want to look at asymptotes, stationary points, and intercept points. So let's break that down into bits, and we'll start off with asymptotes. So let's do that. We'll put a wee heading, asymptote. There's two types of asymptotes. There's vertical asymptotes and then the horizontal or oblique. So let's start with vertical asymptotes. We can say that vertical asymptotes exist when the denominator is equal to 0. We've covered this over the last wee bit, so we can say that there's a vertical asymptote when x equals 1, i.e. the equation of the asymptote is x equals 1. Okay, and what we'll do is we'll draw a dotted line to represent it. We should get my line tool. There we go. We'll get a dotted line to represent it, and we'll write in x. Oh, we have gone, and then there we go. X equals 1. Now we want to check the nature of it. What's happening just to the left and to the right of that asymptote line. So we want to think about x just when it's less than 1 and x just when it's greater than 1. So what we want to do is to check this original function here. So f of x is 2x squared plus 1 minus 1 over x minus 1. Want to factorize that if we can. On the top, it helps to easier to work out the signs of values. So we can factorize that as 2x and x, and we want factors of -1 at the end. So it's going to be 1 and 1. Which one's going to be negative? In order to give a positive x, that's going to be -1 and +1, or however you like to factorize things. And what we want to check is what happens as x tends to just less than 1, just a value less than 1. What happens to y? Well, y tends to a value of, what happens on the top, say 0.9 for instance. Then in the first bracket, 2x minus 1, double 0.9. Minus 1 is going to be a positive value, so there's going to be a positive number there. If x is just less than 1, that second factor is going to be positive. And on the denominator, just less than 1, like 0.9, subtract 1 is going to be negative. So what that means is that overall it's going to be positive divided by negative. So it's going to tend towards negative infinity. And that tells us that just to the left, just before 1, it's going to head down towards negative infinity like that. And as x tends to a value just above 1, like 1.1, then what happens? In the numerator, the value of the first number, 2x minus 1, is still going to be positive. And so the second one, x plus 1, still going to be positive. But the denominator here, if x is just over 1, subtract 1 from that, you'll get a positive value. So I've got a positive numerator divided by a positive denominator, which gives me a positive value, which tells me that as x tends to 1, just over 1, it's going to be up as a positive value. It means it's going to be up towards positive infinity. So that's my vertical asymptote. Let's look at non-vertical asymptotes. Well, we can do a little bit of checking out because it's the order of the numerator is 2, it's an x squared term, and order on the denominator is 1. That tells us it's going to be an oblique asymptote. But we can check that out anyway, but it's good to be able to predict that. What we want to do first of all is do a little bit of algebraic long division and get a quotient and remainder. So we want to divide 2x squared plus 1x minus 1 by x minus 1. So we take the highest order term, 2x squared, and divide it by x. 2x squared divided by 1x is going to be 2x. So we'll write the quotient in there, multiply 2x by x minus 1, and we get 2x squared minus 2x. Subtract that, that gives us 0 here. 1x minus negative 2x is positive 3x. I've still got the minus 1 to bring down here, and so we've got 3x divided by x is positive 3. Multiply 3 by x minus 1, and I get 3x minus 3. If I subtract that, I get 0 there, and I've got negative 1 minus negative 3, which is positive 2, and I can't divide anymore. So I can rewrite my function as being, I can rewrite my function as 2x plus 3, that's the quotient. The remainder is 2, so it's positive 2 over x minus 1. That's a different way of writing the function that's going to help me. So what we can say with regards to that is that as x, so we're looking at here oblique, a wee heading, oblique asymptote. We can say as x tends to a very large number, then y is going to tend towards, what's the y coordinate is going to tend towards just 2x plus 3, because we know that effectively what's going to happen is that that fraction 2 over x minus 1, as x gets very large, 2 over a million minus 1 is going to be a tiny, tiny number. So what happens is that fraction value tends towards 0, and the y coordinate is going to tend towards 2 times the x plus 3. In other words, the oblique asymptote, the equation of the asymptote is going to be y equals 2x plus 3. Okay, so we've got the equation of the, oops, that should have been a line. The equation of the asymptote, let's get rid of that. It's the equation of our asymptote. There's the equation of our vertical asymptote. We'll come back to those. Now, here's my, oops, that's not, my oblique asymptote has a positive gradient, so I'll just draw it in like that as a sketch, and the equation is y equals 2x plus 3. We want to check its nature. So what do? We want to check the nature of that, and in this case here we're looking for values of x as it tends to negative, or y as it tends to negative infinity, and as x tends to positive infinity. So as x gets very large, that's in positive infinity, then, oops, just put a plus in at the beginning of it. As x tends to positive infinity very large, what happens to y? Well, we know that y tends towards kind of 2x plus 3, but what's is the 0? Is it a 0 plus or 0 minus? Well, if we check the original function up at the top, 2 over x minus 1, when x is large and positive, the fraction is going to be 0, but positive, just a value slightly over 0, so we can say that it's going to be, the y coordinate is just going to be a fraction above what it would be if it were on the line 2x plus 3. In other words, we're saying that the actual y coordinate is above the line. As x tends to a very large and positive number, it's going to be above the line, so it means the asymptote is going to be above the line at the end. And let's check as x tends towards negative infinity, y is still tending towards the line 2x plus 3, but is that 0 positive or negative? Well, going back to the fraction 2 over x minus 1, 2 over x minus 1, if x is negative, then it's going to be heading towards 0, but it will be a negative value. So it's going to be just a value just below 0, which also then means that the y coordinate is going to be just below the line y equals 2x plus 3. It's going to be down underneath the line, so the asymptote is going to kind of drop in from underneath. So that's got the nature of our asymptotes. Then we can think about stationary points. So let's bring up a little bit of space here and think about stationary points. Hopefully you should be familiar enough with stationary points. Now we can say that stationary points exist when f dash x equals 0. What was the function? Now let's go with the revised function, 2x plus 3 plus what was it, 2 over x minus 1. It's much easier to differentiate that than the original rational function, because we'd need to use the quotient rule and stuff. We don't really need to for this one, because of course that's just 2x plus 3 plus 2 times x minus 1 to the negative 1. And if we differentiate that, 2x goes to 2, 3 disappears, and if we differentiate this function here, negative 1 times 2 is negative 2, multiplied by x minus 1, reduce the power by 1, and multiply by the derivative of the bracket, or the coefficient of the x term, which is just 1. So we don't have to do anything there, and we'll end up with 2 minus 2 over x minus 1 squared as our first derivative. So if stationary points exist when that is 0, we can say that stationary points exist when 2 minus 2 over x minus 1 squared is equal to 0. How do we do that? Well, if we were to add that fraction to both sides, effectively we'd end up with that. And if we were to multiply both sides by x minus 1 all squared, we would get 2 times x minus 1 all squared equals 2. Divide through by 2, x minus 1 squared equals 1. Okay, there's other ways to think about that. We could just have gone with the idea that in order for that equation to be 2 minus something equals 0, then that would have to be, value would have to be 2, which means that x minus 1 squared would have to be 1 there. So you can rearrange it, or you can just by inspection work out the denominator had to be 1. Wee tricky thing here, because it's very easy to lose a sign, you could just say, oh well, take a square root of both sides and say that x minus 1 is equal to the square root of 1, which is just 1. But please remember that if you're taking the square root of both sides, that the square root of 1 is plus or minus 1. So you'd have to write x minus 1 is equal to 1 or negative 1. Which gives you two answers, x equals 0 or x equals 2. And that's important. There's two stationary points. We can find the y coordinates of these stationary points. So we can say when x equals 0, y equals, well, we can put it into any of the forms that we've got, but if we use just the form that we have at the top of the screen there, 2 times 0 plus 3 plus 2 over 0 minus 1, then that gives you 3 minus 2, which is 1. And if we've got when x equals what 2, y is equal to 2 times 2 plus 3 plus 2 over 2 minus 1. That fraction there has a value of 2. So you've got 4 plus 3 plus 2, which gives you 9. In other words, we have two stationary points, 0, 1 and 2, 9. Now we want to check the nature of these, so let's just do that. We could draw a nature table, but we could also try the second derivative. Okay, so if we check the nature of the stationary points, we use the second derivative. So the first derivative is 2 minus 2 times x minus 1 squared. Second derivative is going to be the 2 differentiates to 0, so we're differentiating this thing here. Negative 2 times negative 2 is positive 4 times x minus 1 to the power negative 3 multiplied by the coefficient of the x term, which is just 1, and so that's our function. Therefore, what have we got? That looks like that's 4 over x minus 1 cubed. Okay, so we want to check the second derivative for each value of x. So when x equals 0, the second derivative is going to be 4 over 0 minus 1 cubed. That's negative 1 cubed. That's 4 divided by negative 1, which is negative 4. And that is, it means it's a maximum turning point at x equals 0. Okay, remember if we check that if the second derivative is negative, it means that it's concave down, which means that it's a maximum turning point. Excuse me. Yeah, and so I just had a wee lapse there. And when x is 2, if we put 2 in to the second derivative, we end up with 4 over 2 minus 1 cubed, which is positive 4, which indicates that it's a minimum turning point at x equals 2. Okay, so we can put all that together. In other words, as far as our stationary points go, we can say there's a maximum turning point at 0, 1 and a minimum turning point at 2, 9. Okay, so that's some more information that we need to bring in to bear. And the last thing we want to work out are our intercepts, if they exist. Right, and we know we've got two things that we need to work out. We can say that x-intercepts when y equals 0 and y-intercepts when x equals 0. And we can work out both of these from the original function. So when y equals 0, let's go into what have we got in our function. You can use either one. Y equals no, probably for this one we're going to be better off using the original rational function. So the original function was basically y equals 2x squared plus x minus 1 over x minus 1. And what we're saying is that we want that to equal 0. And which means that if you multiply both sides by x minus 1, we get 2x squared plus x minus 1 equals 0. We already factorised that up above. I could have used that original the factorised form already. What was it? I'm just scrolling back up. Whoa, it seems like a long time ago. 2x minus 1 and x plus 1. 2x minus 1 and x plus 1. I could have done that again, but trying to save time. So we can say that either 2x minus 1 equals 0 or x plus 1 equals 0. So our solutions there are x equals a half or x equals -1. So that's our two intercept points. On the that's got a half 0 and -1 0. And our y-intercept when x equals 0, that's a wee bit easier to work out. We can use the same one, y equals 2x squared plus x minus 1 over x minus 1. When x is 0, we've got 0 plus 0 minus 1 over 0 minus 1. So you get -1 over -1, which is +1, i.e. we've got an intercept point at 0, 1. So we've managed to do a whole lot. We've done 3 different things in this example. We started off working out asymptotes, the equation of a vertical asymptote, and then the equation of an oblique asymptote with its nature. We then worked out stationary points and their nature and their y-coordinates, and then we worked out intercept points. Well, so we're ready to draw the graph of the function, and we're just going to have to pull in all of that information. So let's draw our axes like that. Is that very straight? I don't think that's straight. It should pop. There we go. So what have we got? I've got a vertical asymptote x equals 1. Now it doesn't. It's hard to know what 1 is from the origin with the other things that we've got to do. So don't worry about the exact scale, but it is okay to draw a second graph if you don't like the first one. So we've got the equation x equals 1. Okay, x equals 1. And the other asymptote is 2x plus 3. Y equals 2x plus 3. So that's a sloping line, obviously, and it's meant to be cutting the y-axis around about 3. But so say it's somewhere like that. It's got a gradient. It's maybe actually a bit steeper, but we're not going to get hung up on the gradient and the likes. Okay, so as long as you note in on the graph key points. So I know that that's going to be 3. There's my y coordinate and x-axis. The equation of my asymptote, y equals 2x plus 3. And that's me. I can add in the nature. Remember, we worked out that on the vertical asymptote, it's going to be going like that, and also like that. And the horizontal asymptote, like that, and like that. Below to the left and above to the right. So we've got turning points as well. Turning point was the point. What was the turning point? Max turning point is 0, 1. That's on the y-axis. So there's my turning point here. Let's say at 1. I'll mark that as 0, 1. So we've got a turning point, and this is where it's not going to be very good on this tablet, but we've got an asymptote there and a curve that comes up and then goes back down. Okay, I could probably spend a little bit of time neatening that up. I don't think that's a word, but just make sure it doesn't hit the line. I've already said in the last example that it is really important that you respect the asymptotes. It shouldn't go away from it, nor should it touch it. So it's about taking a pencil and doing your best to bring it towards. That's going to do it. And on the other side here, I'm going to leave it like that just now, but okay. And that's my turning point. There is the point 0, 1. And my other curve's actually up here. You can see the shape of it there. The other turning point was actually there, and that's the point 29. So I've got the turning point at 0, 1, minimum turning point at 29, and I've got 2 intercepts at -1 and +0.5. And that looks like all of the information that I can actually put in other than the name of the function, y equals 2x squared plus x minus 1 over x minus 1. Okay, so let's try and get a line that's not dotted. There is my function, and I've got my graph, and I put everything in it that I've worked out. Again, you can check it on a graphing calculator if you've got access to one. That would be really good. Okay, so thanks for sticking with me. It's a long exercise, but hopefully you can become proficient at doing these and getting all these bits sorted. Okay.